Sure. Yeah. So welcome everybody to this really last session of the year, corresponding to the junior talks. So the first speaker today is going to be Patrick Flynn from Brown, and he's going to talk about the asymptotic behavior for Vlasov-Poisson via the pseudo-conformal transformation.
All right, thanks for the introduction, and thanks to the organizers and audience for making this a possibility. This has been a really interesting series of talks that I've enjoyed a lot, so I'm happy to contribute something. So I'll start off with just describing a general problem. Consider a continuous density of matter interacting via classical gravitation, so Newtonian gravitation. And so some situation that might be explained by such a setup would be this helix nebula that you see on the left here. So here we have a bunch of particles, billions and billions of particles all interacting with each other, very spread out. And so to good approximation, we can say that really this is some continuous density of matter. And these particles are dispersing and settling into some asymptotic dynamic as time goes to infinity. And we want to understand what this asymptotic dynamic is and when and how it settles into this asymptotic dynamic. And so to leading order, what is the behavior as time goes to infinity? And then another question we can ask is, once we know what this asymptotic dynamic is, can we reconstruct a solution which converges to some prescribed asymptotic data at t equals infinity? And so these sorts of questions are in line with what is often called the scattering problem. So, I mean, this is a general question in PDs, but also just in general physics and dynamical systems. So where it originates is, of course, physicists would shoot some particle at a potential well, and at very early times, we know exactly what the dynamic is. It's just going to travel in some straight line. And at very late times, we know that after it's passed through the obstacle, it's also going to be traveling in some straight line. But of course, physicists want to understand how to compute the outgoing trajectory from the incoming trajectory at, in some way that neglects the complexity of the dynamics as it passes through the obstacle, which in general might be very complicated. And so, of course, this is very general. There are tons of systems, physical and not physical, where for intermediate times there might be some very complicated dynamic, but the dynamics are often trivial as you take time to plus infinity or minus infinity. And the scattering problem is exactly this. How do you compute the data along these trivial dynamics before and after it's passed through some region of phase space where the trivial, this asymptotic approximation fails? And so for our case, we're not going to be considering a single particle, but actually a huge number, a huge collection of particles all interacting through Newtonian gravitation. And instead of obstacle, you notice I put quotes here. It's not really an obstacle, but the collective effects of these particles interacting with each other. And so there's some region of phase space where this, and in fact, the entire phase space, where the particles are interacting with each other in a very complicated way. But as time goes off to infinity or minus infinity, we expect the particles to settle into some dynamic which is actually quite simple, even given this nonlinearity. And so in order to find this map, which takes time at the data at time at minus infinity to the data at time plus infinity, we break it up into two problems. So the construction of the scattering map is ultimately a composition of two maps, which can be described in the following way. So the first map, you just want to show that solutions scatter along some simple dynamic as time goes off to infinity. And so this takes you from the set of solutions to the set of asymptotic data. So the first problem is to establish that given a solution with appropriate conditions, then we have a global and time solution which settles into some asymptotic dynamic, and we can recover the asymptotic data. The converse problem is the construction of wave operators, which is what I'll be focusing on today. So the converse problem is then, if we prescribe an asymptotic data at time plus infinity or minus infinity, then we can reconstruct a solution with this that converges to this asymptotic data as t goes off to plus infinity or minus infinity. And then once we have both of these maps, constructing the scattering map from t minus infinity to t plus infinity is just a matter of plugging your data at t minus infinity into the wave operator to get a global solution, and then using what we know about how solutions scatter to show that our solution will settle into some asymptotic dynamic at t plus infinity, and then recover the data at t plus infinity. And one last piece of terminology. So there's scattering, and then there's modified scattering. So typically when you talk about scattering in the context of PDEs, we really mean that the trivial dynamic followed at t plus infinity or t minus infinity is the linearization. But for this system, because of the long range effects of Newtonian gravitation, there will be a nonlinear correction term to the dynamic at t plus infinity or minus infinity, which will still be very simple, but ultimately non-trivial. So we say that Vlasov-Poisson has modified scattering to emphasize the fact that, in fact, we don't have the linear dynamic. It doesn't settle into linearized solutions as t goes off to infinity. Okay, so I should probably introduce the model at this point. So the model we consider is the Vlasov-Poisson system. It's simply a density. So we have a measure of particles with a density mu squared on phase space. So x and v are x position, v is the momentum / velocity. They're the same up to constants, which we normalize to 1. And so mu will satisfy this transport equation, which is just transport under the force law of Newtonian gravitation. And this vector field can be divided up into two parts. One is the linear part, which is just the vector field corresponding to a free particle, so an unforced particle, and then a nonlinear part, which includes the self-interaction between other particles. So this accounts for all the forces exerted on a single particle. And so this first order ODE has characteristics which follow the trajectory of a test particle in this gravitational field. And so E here is our gravitational force field. Phi is the potential found through Poisson's equation, hence the name Vlasov-Poisson. And then and if we wanted to, we can recast this whole system, so at least the transport equation, in terms of Hamiltonian transport by a Hamiltonian vector field. So rather than write out this transport equation here, we could say that mu satisfies mu t plus the Poisson bracket of mu and h, where h is the first Hamiltonian any physics student ever learns. It's just the usual kinetic energy, v squared over 2, plus the usual potential energy, which is this potential field given by solving Newtonian gravitation. Okay, so a bit about what we mean by modified scattering in this case. So what we mean by this is that characteristics as t go off to infinity don't correspond to the linearized equation, which is the free transport equation. So a free transport of a free particle. And so if the linearization held at t plus infinity, then the characteristics of our transport equation would correspond would just be some position x infinity plus a constant velocity v infinity. But in fact, as you can see, there's some logarithmic correction term in the characteristics for x. And so this E infinity is we can think of this as an asymptotic electric field, although the electric field decays like 1 over t squared. And so in order to recover this E infinity, we have to rescale E by t squared and evaluate it at vt, and we recover this function E infinity. And so a couple questions you might ask is, where is this coming from? Why log t and why 1 over t squared decay for E? And this can be explained through a fairly simple heuristic argument. So for Newtonian interactions, any two particles moving away from each other at mostly constant velocity are going to exert a force on each other like 1 over t squared, right? So for Newtonian gravitation, Newton's law of gravitation tells us that any two particles will exert a force on each other proportional to 1 over r squared, where r is their distance. And if their distance is growing like t, so a constant times t, then the force they exert on each other will be like 1 over t squared. And so we can compute so this 1 over t squared tells us the leading order behavior of the acceleration of any given particle. So when we integrate this once in time, we figure out what the change in velocity will be. And so this will be of order 1 over t. So this causes a 1 over t correction in the velocity, which is not felt at t plus infinity, because 1 over t converges to 0 as t goes to infinity. But when we integrate this one more time, we have an appreciable effect on the trajectory for x, which will be logarithmic, right? If we integrate 1 over t, excuse me, we get log t. And so that produces this logarithmic correction term in the characteristics for x. So this is all heuristic, but in fact, we can make this rigorous. So for small initial conditions, mu0 in an appropriate Banach space, the solution with this initial condition to Vlasov-Poisson will be global, and it will actually converge to some fixed density mu infinity if we subtract off this, if we subtract this off x in the argument for mu. So basically, to leading order, the characteristic variable for mu will be this quantity here. And this tells us that as t goes off to infinity, we recover a fixed density along these trajectories written out before. And of course, we have convergence of e to e infinity in the sense written out on the previous slide. And in fact, this e infinity is related to mu infinity by the following, by this formula here. Now you'll notice that this is almost the same formula, which gives e from mu, but with the important difference that the roles of x and v are switched. So in order to compute e from mu, we had to integrate in v and take an inverse Laplacian in x and take a gradient in x. But now we're integrating in x and we're taking an inverse Laplacian in v and a gradient in v. And so if you want to understand this better, here are a list of papers you could consult. Okay, so that's what's been proved already. This is the modified scattering part of the pictures, so showing that solutions scatter. The other piece of the picture is to show that we have some sort of modified wave operator so that we can construct the scattering map. And in order to do this, first, here's the result. So given mu infinity in an appropriate Banach space without any smallness condition, I should note, and e infinity given in terms of mu infinity in the same sense as the previous slide, we can construct a solution mu which converges in exactly the same way as written on the previous slide. So the converse problem has been solved essentially. And so this is joint work I did with Jimeng Oeng, Benoit Pausader, and Klaus Widmeyer. All right, so I should probably talk a bit about the pieces of the proof. So the first tool we use is this pseudo-conformal transformation, which allows us to invert time. So the pseudo-conformal transformation is something that's been used very extensively for nonlinear Schrodinger equation to analyze either blow-up solutions or long-time dynamics of nonlinear Schrodinger equation. And it's advantageous because it places the infinite time horizon at 0. It's only been used, to my knowledge, once for Vlasov-Poisson, but nevertheless it can be used for Vlasov-Poisson. So we get this time inversion formula for the Vlasov-Poisson equation. So in defining a new spatial coordinate q and a new momentum coordinate p and inverting time, we get a map which takes characteristics of free transport in the original coordinate system to characteristics in the free transport equation in our new coordinate system. And so one might hope that this also preserves the nonlinearity of our equation as well. And it almost does, with one major flaw. So if we set gamma equal to mu, just expressed in our new coordinate system with this inverted time, we get almost the same so we almost get the same equation, it's almost Vlasov-Poisson, with the major difference that the potential, so you'll note that psi is the potential induced by gamma in the same way that phi is induced by mu. But the major difference is the potential energy term now has a 1 over s. Oh, am I out of time? I heard a beep.
It's 19 minutes. So
19 minutes. Okay, well, I have 2 more slides. So we want to study the limit as s goes to 0, but s inverse is not integrable. So in order to get around this, we we remove this 1 over s singularity using a canonical change of coordinates. So set F to be our new electric field in this coordinate system. There's a simple relationship between phi and psi and E and F. We assume convergence of psi and F to some limiting potential and force field, psi 0 and F0. And we define this type 3 generating function here. And so how you might think of this is that this is a leading order approximation for the action near s equals 0 if we insert w equals to q. And when we do this, so we get a new system of coordinates w and z. W is incidentally just equal to v, so our original in our original coordinate system, and z is equal to this leading order expression for the characteristics at t plus infinity. And now we get a new Hamiltonian system. So transport by a Hamiltonian vector field by expressing gamma in our new coordinate system through sigma. And with a new Hamiltonian k, which is now a difference quotient. So we have some translation of w by e, where e is of order s log s. And so this difference quotient may blow up logarithmically in s, but of course for local existence theory, for ODEs, Picard-Lindelof, everything works if we assume that the vector field is only L1 in time. So in fact, this logarithmic singularity is perfectly okay from our point of view. And okay, so I'll just cap it off talking a little bit about the analysis. After this point, we really just try to solve this this transport equation so solve the Cauchy problem for this transport equation at s equals 0. We use the fact that transport by Hamiltonian vector field is volume preserving very extensively to get estimates like this in LP spaces. This makes bounding moments in LP spaces fairly easy, which are plugged back into bound F. But bounding similar norms to the gradient of sigma which is necessary for uniqueness and getting strong solutions is quite a bit harder. There's some loss of moments phenomena that happens, which we get around through localization in phase space. Anyways, sorry if I went a little bit over time. Thanks for your time.
Thank you.
Incidentally, I've been lax with the muting standard, so everyone already has the ability to unmute themselves.
One quick question or comment for Patrick?
I have one. So if I understand correctly, so everything is just this sort of cloud of particles. They're interacting via self-gravitation, right? But they're still scattering. This is what you're showing. Okay, so I was curious, would you be able to also perhaps introduce a sort of, for lack of a better term, an external potential? Like for instance, what if you had, like a massive body, a planet or something like that, that was also serving to sort of attract the particles? Would you also expect scattering in this case, or would they perhaps just end up being bound states orbiting the planet or whatever?
Well, it's a very good question. So as far as I know, Benoit and Klaus are working on this, and
oh, okay, never mind.
it's not well understood, but at least these transformations are not, the fact that we have a continuous density is not important from the point of view of whether or not these transformations work. And so in theory, these canonical transformations would work for n particle systems or a mixture of a Dirac mass type measure and a continuous density.
Thanks.
Okay, so we are a little bit tight on the schedule. Maybe let's thank Patrick again, and we'll keep moving.
Yeah, thanks everyone.
Okay. Okay, can you see my screen?
Yeah, that's perfect. So our next speaker is Milan Ivanov, also from Brown, who's going to talk about reaction diffusion systems.
Okay. Well, thank you to the organizers for giving me the opportunity to talk on the seminar. And today, like, I'm going to talk about the results from my thesis on reaction diffusion systems. This work was done in collaboration with my advisor, Björn Sandstede from Brown University and Professor Arne Schild from University of Minnesota. So my plan for this talk is to give a brief introduction and motivation for the problem, and then I'm going to introduce spatial dynamics from reformulation of the problem, which has been mentioned on this seminar before a couple of weeks ago. And well, then I'm going to talk about the Galerkin approximation of the problem of a problem we reached to, and then I'm going to present two main results. One on existence and uniqueness, and one on stability. Then I'm going to, time permitting, I'm going to give the idea of the proof of spectral stability, and I will wrap it up. So the object of study are these spirals which are shown here. So I have on the first picture we see a spiral wave. However, this spiral wave has a defect. Namely, there is a jump for well, like if this was an ordinary spiral, like we would have, let's say, two colors, just yellow and ordinary blue. However, this spiral underwent a a period doubling bifurcation, and experimentally and numerically, you would say that under such behavior, all of a sudden there is a jump from a small crest to a large crest, like over here, like presented over here. And that's just the behavior which we observe numerically and also experimentally. So, well, the question is, what do we like? How do we talk about this? And one way to try to study this phenomenon is to say, well, let me take the spiral and let me slice it with a knife, going upwards, and then I can grab this and I can wrap it around a little. So if I do a cut over here, and and apply some imagination, I can say, well, over here, like in an abstracted version of this setting, I'm going to have some place where my wave jumps half a period, and on the end point, I'm going to have something which is periodic, with some and. This is the object I want to talk about. This is the object which I'm studying. So we see that well, we have a defect, whatever defect means. We have a defect over here, and it is posed on, let's say, on a large interval -L to L. And let's say I gave it either periodic or Neumann boundary conditions. Like maybe there is a jump of half a period over here. But when I go on towards the endpoints, the periodic conditions are going to match up. So the abstracted version of this picture is one-dimensional defect with some boundary conditions. Which and now, well, I should mention what is a defect, like more formally in terms of the work of Björn and Arndt. So the defect we're talking about, where we have a reaction diffusion system where x one spatial variable, one time variable, and we have the key properties. Here I have time periodicity. So and well, the diffusion matrix is diagonal, positive entries, F is smooth, so on. Like we can relax this a bit, but where we can relax the C-infinity assumptions, but whatever. So in order to say what the defect is, well, I'm just going to I'm going to talk about contact defect is, which for the purposes of this talk, contact defect and defect are the same thing. So I'm going to say, well, let's say that my system has a family of periodic solutions, which we call wave trains. UWT stands for wave trains, and let's say that I have they are of kx minus omega t and parameterized by a wave number k. And then informally, what we mean by a defect defined on R is a solution of this reaction diffusion system, which at plus and minus infinity looks like a wave train, but it is not. Right, so that's informally what a defect means. And the formal definition of a defect, of a contact defect, will be, well, here I would have a time periodic function of some frequency, and if I give it a small phase correction function theta, my defect evaluated at x minus theta of x, and t is going to converge to my wave train as x goes to infinity, converging in the C1 norm on the unit circle. But yeah, so and yeah.
I'm sorry, Milan. Can I interrupt and ask a very simple question? So
Yeah.
here it looks to me like you're saying your spatial domain here is one-dimensional, but on the previous slide you were showing us 2D plots.
Uh-huh.
Are these plots like space-time plots, or what are we looking at?
Well,
here?
this is a snapshot of frozen in space. Yeah, that I should have explained that. That's a snapshot of a spiral frozen in space. So when you observe it, when you observe the numerics, it's going to rotate. So here I took a frozen snapshot, and I abstracted it to this. So here and over here, I'm going to take basically this vertical direction of time. So I'm going to have one space in one time dimension by virtue, and this one has two spaces in one time because I just froze the time here.
Okay.
Yeah.
Gotcha.
I should have explained this. Thank you for the
Thank
question.
you.
So so informally, like a defect is something which at plus and minus infinity looks like a periodic function, but it is not in itself. So my goal is, well, I explained what is a defect for x on negative infinity to infinity. So now I want to take such a defect and I want to truncate it to negative L to L. That is, I want to say, well, first, we'll need to do some explaining when one function is on negative L to L, the other is on R, for x is on R. Well, they have to be close somehow, and I have to explain what close means. And for the I want to give this boundary conditions, let's say periodic or Neumann. So a question of interest will be, well, does this thing exist whenever L is large? In what sense it is unique? And what can I say about the stability? And well, before that, the general approach we take is the so-called spatial dynamics. So we can grab the reaction diffusion system, and we can rewrite it as a first order ODE where x is my evolution variable. And so the tau derivative is going to come up over here on the right hand side. And I have not written down the spaces, but these are Sobolev spaces, or well, this is an ill-posed system on Sobolev spaces of the unit circle. So h1 times h1 half, let me on the unit circle, let me not go into details, but that's an ill-posed system over here. And for the right frequency omega, which I vary, right? My wave train, like each individual wave train, is going to be an equilibrium of the right hand side, yeah, because it turns out that this wave train is time independent, is x independent. So, and well, this right hand side, it has translation invariance, because whenever we have, let's say, L2 of the unit circle, I have a translation operator. So if one particular wave train is an equilibrium, the set of its times translates is going to be a circle of equilibrium. which I depict on this next picture, which really illustrates the whole dynamics of that thing, right? So I have a circle of equilibria, and then, well, let's recall a defect, like up to a phase correction, a defect is going to converge to a wave train. In other words, what turns out that my contact defect is going to move and is going to converge, spin around and converge to the circle of equilibria. Now you may ask, well, can you just go in a regular pattern, like just converge? And the answer is no. In our case, because this phase correction term actually is logarithmic. So it actually turns out it's a very similar behavior to what Patrick Flynn described in his previous talk. Well, similar in the sense that we have the phase correction is small in the sense that its derivative is like 1 over x, and it goes to 0. But when you integrate it, you get a logarithmic divergent term. And this means that when the contact defects approaches the circle, it's going to rotate more and more, spinning infinitely often. And the same behavior also is going to hold as x goes to -infinity, but I didn't draw it for clarity. But really, like this torus this dynamic series, the gist of what's going on in this talk. And well, and briefly like to mention, for this infinite dimensional system, well, if it's like it turns out it could be a bit too complicated to study. So so if we consider a Galerkin approximation, let us just project it to the first couple of Fourier modes, and we're going to get a large system of ODEs. And the key thing is that my translation by time, like which generated the circle, and the translation which is valid everywhere, of course, in this picture, is going to give us symmetry by the circle group on this large system of ODEs, or if you prefer, you can call it a representation, a group representation. And that that non-linearity is going to behave nicely with respect to this symmetry, e to the alpha a. And the point is that well, I'm not going to go into details, but the geometry of these things is still going to be a torus. So here are my my main results for here are the main results. Like under reasonable assumptions, if you give me a large enough L, like the spatial dynamic system, this time in finite dimensions, it has a periodic function, periodic solution, which is defined to negative L to L. That is O of L to the negative 2, close to the torus, which I discussed just now. And like that solution satisfies my both periodic and Neumann boundary conditions. And and moreover, the uniqueness part is that that solution is unique up to translation. And well, I need to pick this parameter omega. That omega is uniquely determined as well by L. So that is the essence of this result. Well, the essence of this result is that I can start with this trajectory, and when I perturb, like there is this so-called normal hyperbolicity. This torus is normally hyperbolic. So when we perturb it, when we perturb the system, the torus is preserved. However, it turns out that the circle of equilibrium disappears, which you can see by the equations. So instead of rotating infinitely often, at some moment the solution is going to pass through and then go on, and return back where it started. So, and fundamentally, like this gives me this is an existence result, which tells me this is the result which explains to us where does this existence comes from, and it's, as we see, it's very geometric. Yeah, so normal hyperbolicity is the key ingredient. And the second thing which we want to mention is well, we want to construct an eigenvalue problem, which time permitting later I can mention how we get the eigenvalue problem. But like here is the lambda, which we're worried about, and we want, we get it roughly, we get it through Fluke theory. So lambda is actually it's a Fluke exponent, and for spectral stability, we want the Fluke exponents to be in the left half of the complex plane. And the stability result is the Tower function, which we obtained before, is spectrally stable when I give it periodic boundary conditions, and 0 is an eigenvalue of multiplicity 2, which means that the space and the time derivative, which are like given by the symmetry, they are both eigenvalues. However, if I give it normal boundary conditions, we're going to get spectral instability. And lambda is going to be an eigenvalue of multiplicity only 1. And the other multiplicity is going to drift a little in the right part of the complex plane. The double eigenvalue, which I mentioned here, is a single eigenvalue, and we get an unstable eigenvalue as well. Okay, so how am I doing time-wise?
3 minutes and 20 seconds.
How many, sorry?
You're 16 minutes.
16 minutes.
Almost 17 minutes.
Okay, so briefly, like I'm going to briefly mention how we prove spectral stability, and then I will wrap up. So the main idea is that I have a reduced equation on the center manifold, on the center manifold that is on the torus, which I can write down. And without getting into too much detail, that's for the dynamics on the torus, and that's for the dynamics on the A and B are for the dynamics on the tangent space. So the key ingredient is if I substitute V B over A in this linear, these are linear in A and B in this equation, we're going to have an equation on the projective space, and then we want to rescale the parameters omega and lambda appropriately. So, and if we rescale them appropriately, then the resulting system of linear equations its leading terms are homogeneous of order 2, like epsilon squared and y squared, like all of the red terms, they're homogeneous of order 2, and of course I can think of the 0 also as homogeneous of order 2. And therefore, this allows us to study to do the so-called blow-up methods, which roughly like, well, I went to the projective space, and these blow-up methods allow me to study two phenomena separately. Over here, first I can study this with one chart. I can study on the projective space. I can study this saddle node bifurcation, which is not very pleasant, and we want to convert to a hyperbolic system. And in another chart, I'm actually able to write down my boundary conditions. And in this later rescaling chart, which we call it, I can write down properly the boundary conditions, and it turns out in there I get an irregular Sturm-Liouville problem, which is like after this is like after a lot of computations, but this gamma naught squared, which is coming from my lambda, from my eigenparameter. This eigenparameter is also present in the boundary conditions. However, we can still get, like everything else like this. Other than that, this is almost the Laplace equation. So it's a very nice system overall. So we can still get results for it. And here is some geometry for which I think I don't have time to talk. So let me just say what like plans for the future. Well, we want like you would remember that I mentioned the Galerkin approximation, and now we want to extend this to fourth generality to the fully infinite dimensional setting, which we would use like something slightly different than normal hyperbolicity in these infinite dimensions. However, the stability proof is going to remain the same. because fundamentally it's a center manifold reduction. Then questions which we want to ask is, well, linear and nonlinear stability after spectral stability. And well, what can I say about this spiral wave over here? Like in a little more detail, because there could be like not only one, there could be also 3 defects or 5 defects and so on. So that's all I have to say for now, and thank you very much for your attention.
Exactly 20 minutes. So.
Perfect. Questions or comments for Milan?
Yeah.
No?
So Milan, just one question. So you, in the end, you studied the PD in finite dimension by restricting to finite Fourier modes?
Yep.
Okay.
Yeah.
And so do you think you could go to infinite dimensions then to really get the PD?
Yes. So in infinite dimensions, like it wouldn't be exactly normal. So let me just go back a little. So this picture, it also holds in infinite dimensions. However, I cannot really perturb it. Well, it would be kind of difficult to perturb it in infinite dimensions. However, like you can still like there's still some methods on which we're working on with my advisor to construct to construct a solution when I perturb omega, this parameter omega. In finite dimensions, like I explained this via normal hyperbolicity, in infinite dimensions, we believe it's doable as well. However, the stability fundamentally is center manifold reduction, so it's all good.
Okay.
Okay. Other questions or other comments? No. If not, let's thank Milan again.
Okay. Can you hear me?
Yep, we hear you and we can see the screen. So the last speaker of today's session is going to be Stefano Pasquali, coming from Lund University, who's going to talk about chaotic light transfers of energy in Hamiltonian PD.
Okay, so let me thank the organizer for giving me the opportunity to give this talk. And I will speak about, as the title says, about transfer of energy in Hamiltonian PDEs. First, I will resume some results available in the literature for this problem. And then I will talk about chaotic light transfers, which was a project that I did with the team of Marcel Guardia at UPC in Barcelona. Okay, so the problem of transfer of energy for PDEs was studied for the cubic defocusing nonlinear Schrödinger equation on the 2D torus. Later on, I will call this equation NLS. This equation has 2 conservation laws.
Can you try to make it full screen? Sorry, can you try to make the...
Yeah, I guess it's full screen. It's max that
Maybe
I can.
in view. No, if you go to view.
Yeah.
And then okay, well, I don't know this viewer. Okay, no, it's fine anyway. Don't worry.
Can you try F11?
Thank you. Okay, so the NLS admits 2 conservation laws, which are the energy and the mass. The fact that we have 2 conservation laws leads to the fact that we have that the equation is globally well-posed in the solar spaces HS for s bigger or equal than 1. Moreover, the fact that we have the mass as a conservation laws implies that the L2 norm of the solution is conserved, and the fact that we have the energy as a conservation laws implies that the H1 norm of the solution is bounded. So natural question is what about the Sobolev norm of the solution for s strictly bigger than 1? Burgani in the 90s proved the following upper bound for the Sobolev norm of the solution. He proved that the Sobolev norm of the solution for s bigger than 1 at time t is bounded by t to some power c multiplied c s minus 1 as t goes to infinity. So this was an upper bound on the growth. But some years later, he raised the following problem: whether there actually exists solution, which such that the Sobolev norm for s bigger than 1 goes to plus infinity, and this was a problem of the growth of Sobolev norm for the Hamiltonian PDEs. If one rewrites the equation in the solution in Fourier, one can also rethink or restate this problem of growth of Sobolev norm as a transfer of energy from the Fourier modes with a low frequency to Fourier modes with high frequency. And the first breakthrough about this problem was a result by Colliander, Kirchhoff, Milan Ivanov, and Tao in 2010, which proved finite growth of Sobolev norm for the NLS. So fix s bigger than 1, small delta, and the capital M, they prove that there exists a global solution U and a time capital T, such that the Sobolev norm of the initial datum is smaller than delta, and the time capital T is bigger or equal than M. And this was the finite growth. Later on, Marcel Guardi and Vadim Cauchy improved also a quantitative estimate for the speed of this growth. I will review the mechanism used by Colliander and collaborators to prove this result, because actually the results about chaotic transfer follows a similar strategy. So the strategy to prove the growth of Sobolev norm is divided into 4 steps. The first one is to apply Birkhoff normal form to the equation. So one rewrites the equation in Fourier, and then one makes a symplectic change of coordinates in order to obtain an infinite system of ODEs, on which the nonlinear part is supported on modes which form a rectangle in Z2. The other contribution give only a small reminder. So now we are restricted to an infinite system of ODEs. Next, we make a reduction to a finite system of ODEs, which is called in the jargon toy model. So we restrict to a finite set of modes that we will denote by lambda, which we will subdivide it into generations. At the jth step, we will activate the modes at the generation j, and we will put at rest the modes previously activated. At each step, only half of the modes in the new generation will cause the growth of a Sobolev norm. So at the beginning, the Sobolev norm will be localized in a large number of Fourier modes. So this is actually a plot for 9 generation. You see in yellow, you see in orange the first generation, and at the end, the Sobolev norm will be localized into Fourier modes. This one. Next, one has to prove a diffusion behavior for this finite dimensional toy model. In order to do so, the Colliander and collaborators exploited the symmetry properties of the NLS, and they observed that the toy model admitted a 4-dimensional invariant manifold on which the dynamic is integrable. Moreover, in such invariant manifold, there are 2 hyperbolic periodic orbits whose stable and unstable manifold coincides, and this is just a behavior which is a higher dimensional analog of the phase portrait of a pendulum when you have the hyperbolic equilibrium and the sparatrices. Moreover, there exists also a family of connection which goes from one hyperbolic orbit to the next one. And the diffusive solution is constructed by taking a solution which stays close to the invariant planes and travels close to the connection from a neighborhood of one hyperbolic orbit to a neighborhood of the next one. And this mechanism is called shadowing. Next one is to approximate this finite dimensional behavior by the solution of the original PDE, but this is rather standard, and one can do so by Gromwall lemma and the bootstrap argument. So this was for the NLS. Now, what happens in other PDEs? This was a joint work that I did with Filippo Giuliani, Marcel Guardi, and Paul Martin at UPC in Barcelona. we consider three Hamiltonian PDEs with cubic nonlinearity, which are the cubic artery, the cubic beam, and the cubic wave equation. And we try to apply a similar strategy to the one of Colliander and collaborators. So when making the Birkhoff normal form, we lose the symmetry properties of the NLS, and moreover, we have a small divisor problem with the wave equation. So in order to perform this Birkhoff normal form, in order to simplify the equation, we have to use a weaker version of the Birkhoff normal form to make it convergent. Then, in order to reduce the finite dimensional toy model, again, we reduce to a finite set of frequencies, lambda. For the artery and the beam, the linear frequencies are the same as for the NLS, which are given by modulus of k square. And so the construction of the set is similar. While for the wave equation, the linear frequencies are given by modulus of k, which was the problem of the small divisor problem that we have in the previous step. And now we will restrict to a finite set of frequencies in which the frequencies will form not rectangles but parallelograms inscripted on ellipses. And then we introduce a smaller parameter epsilon in this construction, which will measure the closeness to integrability. Why I mention this closeness to integrability? Because if we restrict the system, the model, to a system of two resonances of four modes each, to this joint family of four modes, we have that the effective Hamiltonian is given by an uncoupled Hamiltonian H0 plus epsilon H1, where H1 gives the coupling between the two subsystems. And so we will consider epsilon as a small parameter, and other parameters appearing in the coupling H1 will depend on the model itself. So on the coefficient of the potential for the artery and on the precise choice of modes for the beam and the wave. Now, for the NLS, if you do this procedure, you obtain that epsilon is equal to 0, and so the system is actually integrable as observed by Colliander and collaborators. This is a phase portrait of what you obtain for the NLS. In general, as I mentioned before, the system is not uncoupled, so it's not, in general, it's not integrable. However, there exist hyperbolic invariant subspaces, but in general, unlike the NLS, their stable and unstable manifold will not coincide anymore. So how can one approach to the problem in this general case? Well, one standard technique in the finite dimensional setting is to find the intersection between the stable and unstable manifold, at least when epsilon is a small parameter, by using Poincare-Melnikov theory. If one proceed in this way, one obtains that the necessary condition to obtain an heteroclinic connection between the invariant manifold is to ensure that the invariant manifold lie on the same energy and the same energy level. So if the Hamiltonian satisfies this energy level condition and an open condition which is found through Poincare-Melnikov theory, which basically reduces into computing integrals, one can prove the existence of an heteroclinic connection between these two invariant manifolds. Moreover, if the Hamiltonian satisfies another open condition, which is again found through Poincare-Melnikov theory, one can prove the existence of homoclinic orbits. This kind of argument works also if we restrict the equation to any finite number of disjoint rectangles. So once we prove the intersection of the manifold, we exploited again standard tool in hyperbolic system, which is the notion of chaotic dynamics. The most famous example of chaotic dynamics is the Smale-Horseshoe, which is given by the shift map on the space of sequences. the fundamental properties of the map is sensitive dependence on initial condition, topological transitivity, so we have dense orbits, and also the fact that the periodic orbits are dense. And we prove that the existence of such dynamic for the system in normal form, the finite dimensional one. And then we approximated the original solution of the PDE. For the normal form, the Newtonian normal form, we proved that the following result. So if n is bigger or equal than 2, then there exist lambda sets which are invariant by the dynamics such that the space V lambda is invariant by the dynamics of the normal form. And for n equal to 2, the flow associated to the normal form can be conjugated to the shift, basically. And moreover, if for n bigger or equal than 2, we prove that there exists capital N tori, which are partially hyperbolic and of dimension 2 to the n plus 1, such that if we take a small neighborhood of this tori and any sequence of numbers, then there exists a solution to the Hamiltonian in normal form and the sequence of time ti, which will depend on the sequences, such that the solution at time ti will lie in the neighborhood of the torus with the index pi. So you choose as neighborhood of this tori and any sequence, so I can find the solution which at times ti passes close to the torus pi. So to summarize, in the first part of the previous theorem, we proved that for the Birkhoff normal form Hamiltonian, there exists invariant set which display chaotic dynamics, exactly like in the finite dimensional case. And in the second part of the previous theorem, we proved the existence of orbits which visit a given set of invariant tori in any prescribed order. This result relies on the existence of a chain of invariant tori, which are this one, connected by transverse heteroclinic connection, which are this one. This one is the stable, and the red one is the unstable. So one can connect this tori by using this connection. One starts close to this torus, then one can travel along this one and this one to go to the second, then to the third one. And one can obtain this kind of behavior for any number of tori and any sequence of For the original equation, we proved the chaotic light transfer of energy. So I studied this theorem for two families of four modes. So we proved that for epsilon small, then for a large choice of 8 modes in Z2, there exists a constant T0, such that for T bigger than T0, if we choose any K and any finite sequence, Mj, then there exists a solution of the original PDE, which is supported on these 8 modes of the set which form the set lambda up to small correction, and such that the first family of 4 modes will display a periodic transfer of energy. So there exists a periodic function Q that approximates the energy of the modes up to an error, a small error. And while the second family of 4 modes display chaotic light transfer of energy, so there exists a sequence of time Tj, which depends on the original sequence Mj that I've randomly chosen at the beginning, such that the energy of the mode at this times Tj is equal to 1/2. And moreover, the energy of the modes will oscillate between order epsilon and order 1 minus epsilon. So basically, one can reproduce this kind of behavior in which the energy of the modes is like a multi-bump-like function, but the energy in the times on which the energy crosses the line 1/2 can be chosen randomly. So what is the difference about the results that we obtained with respect to the one by Colliander and collaborators? Well, the results about Colliander and collaborators gave rise to the growth of Sobolev normal and relies heavily on the fact that the Birkhoff normal form is integrable. So one can find the chain of tori connected by non-transverse heteroclinic orbits, but this phenomenon is highly non-generic, because integrability is a highly non-generic phenomenon in Hamiltonian systems. While our theorems relies on the fact that the Hamiltonian is non-integrable, but close to an integrable one, and the fact that there exists invariant tori with the connection, which homoclinic orbits which are transverse. So the solution constructed in this way do not display the growth. So the instability phenomenon is weaker, but this phenomenon seems more robust than the one by Colliander and collaborators. And these are the two papers in which we studied this phenomenon. Okay, so thank you for your attention.
Any questions or comments for Stefano? No, okay, I do have one. So where exactly are you using that your equations are those particular equations and not like others? Can you prove like what do you actually need to prove such a theorem, like from the equation, I mean?
Well, you have to use the fact that these equations are Hamiltonian. So
other than, let's say, from any Hamiltonian equation, what exactly do you use from the cubic wave or cubic beam?
Okay, we use we use the fact that the nonlinearity is semilinear, so does not have there are no derivatives in the nonlinearity, which will give modification when you write the equation in Fourier. And we are use the fact that the frequencies are given by k modulus of k square or modulus of k. If you have any other law, it will be extremely difficult, and it's actually open whether there exists a finite set lambda which satisfies the properties which are used to both to obtain the intersection between the manifolds, basically. So these properties are specific of the fact of the frequency that you have chosen, and the frequencies in turn depends on the linear part of the equation, which.
So you are not able to do it, let's say, if you had like a different power, let's say k to the 3 halves or something.
No, this is open.
Maybe something related. So why do you need T2? Why not 1D or why not 3D?
So I stated the results for the two-dimensional torus. The results for the higher dimension follows easily just by considering solution which are zero on the other component on the components after the second and the first two components like in this case. While for the one-dimensional case, there are a lot of results about stability phenomenon. So like the upper bounds that like Bourgain made in the 90s, but also many more people working in Hamiltonian PDEs as proven in the later years. And moreover, the fact that we are in dimension at least 2 allows to construct such a set lambda, which always want to obtain growth or intersection between these two manifolds. This construction simply does not as a counterpart in dimension 1. And the fact that there are many stability results is not, does not suggest that this construction is actually a counterpart in dimension 1. So the instability phenomenon for one-dimensional Hamiltonian PDEs on the circle, if they exist, are of different nature than the one that I explained to you.
questions, comments?
Yeah.
Yes.
So around the time you mentioned the construction of heteroclinic connections with the Lynch method, you mentioned shadowing argument. Can you tell us what's that?
The shadowing argument, I mean, it's an argument that is used in hyperbolic dynamics in order to approximate an orbit of a system, and you can use to your advantage the fact that the system is hyperbolic in order to prove that you can construct actually a solution that stay close to it for a long time. In this case, one can construct a solution. You want a solution which visits all the different tori. And in order to construct it, I mean, you rely to the fact that the system is hyperbolic in order for abstract theorem of hyperbolic system can ensure you that there actually exists a solution which stay close to this tori. One can also use, in this case, more refined argument if one wants to be more quantitative. So to say how much close to this tori one can pass, but I mean, this is the idea.
Okay, yeah, but shadowing is like this act of constructing this orbit close to the connections. Okay.
Yeah.
Yeah, thank you.
Anybody else has more questions for Stefano? No? If not, let's thank him again. And thank you all of the speakers today.